Okay, so in our previous video I showed you how to visually see how a binomial distribution can be approximated by a normal distribution. But today we're going to go a bit further and do some examples. Right, so the example that we're going to do is in some sort of medical experiment. We're going to say that that we know that 30% of the patients are cured from some sort of treatment. Okay, so we have now we're going to take a sample of 50 people, okay, a new sample of 50 people. Just remember this 30% is from past data, right? So we know it's 30%, but we take a sample of 50 people and then we're going to ask a few questions. So for example, the first question that I'm going to ask is, what are the chances of only 20, and I do mean only 20 people are cured? That's this one over here. What's the chance of at least 20? And what's the chance of more than 20 people are cured? Okay, so let's start off with the first question. The probability of x equal to 20. Now we know this is a binomial question, so we can do with the binomial method. So I'll show you how to do that way first. Actually, before I do that, I'm going to write down data. So it's quite crucial that you write down the data that you already know before you start off with this question. So I'm going to say that little p is equal to 0.3, the 30%, okay, and n is equal to 50. Okay, now I start off with the question. Okay, so the question goes, find the probability of x equals 20. So if I was doing this in a binomial method, it will go 50 choose 20, 0.3 to the power of 20, and then 0.7 to the power of 30. Okay, so now that's binomial, but that's not what we're trying to do. We're trying to approximate this with a normal distribution. So how do we do that? So I'll show you the normal distribution and the binomial distribution first. So that's a normal distribution. Yeah, okay, that was a bad one, but anyway, I hope you get the idea. And it's being approximated by this. It's approximating this binomial distribution, which looks like this. Okay, so at some point, so in this case 20, we want to know, so 20 would be the midpoint. We want to know the probability of this thing. We want to know the probability of this shape. Okay, so that's the probability that we want to know. That's column, right? But remember, now we're approximating this. So if you're approximating it, what we can say is that the approximation is going to be roughly this area. Okay, so the rest of the normal distribution goes like this. Okay, so this area is my approximation. I mean, as you can see, it's not exact, but it's only a small bit off. Okay, so sometimes, like I happen to draw this above it, but it could have easily been the binomial distribution. See, it could have easily been underneath it, right? It's just a coincidence of the way that I drew. Okay, so it's more like this, where it probably goes half above and half below. Okay, so the question is, how do you calculate this part of it? Okay, so what we're going to do is remember that the binomials are discrete. It goes 20, 21, 22, and so on, right? Whereas normal distribution is continuous. So the approximation, the most logical approximation for x equals 20 in that case would be to say it's between, when we're talking about normal, it's between x is between 19.5, I need some space over there. X is between 19.5 and 20.5. Okay, so look at this. So it's really 20 that we're after, right? it's 20 that we're after, but we take 0.5 on either side to make it as close as possible to this column. Okay, so that's where the 19.5 and the 20.5 came from. Okay, so if you go any beyond that, we start taking out from the 21, which we don't want, right? So that's why I stop at 20.5 and I stop at 19.5. Right, so that's the probability that we're after. Okay, now if you remember about normal distributions and how to find them, we can't directly deal with x's. We need to convert it into z. Now how do I convert it into z? So I'll write down the formula for z. Z is always going to be x minus the mean divided by standard deviation. So we need to standardize this. Okay, so I don't know mu yet, I don't know my sigma yet. Okay, to find the mean of a binomial distribution, it's simply NP. Alright, and I know that n is 50 and I know that p is 0.3. Actually, there's one more step that I need to do. I need to show that I can approximate this with a normal distribution, and to do that I need to find NP, I need to find NQ, which is 50 times 0.7. So remember, Q is simply 1 minus P, and I'll just state what N is. The condition that this is greater than 5, NQ is greater than 5, and this is greater than, if I remember correctly, 30, these three conditions, if they're satisfied, these three conditions combined say you can approximate with a normal distribution. Okay, because if one of these conditions aren't satisfied, you can't actually go ahead with this question, at least not in the normal distribution method, right? So you can't do any approximation. It's only when these three conditions are satisfied that you can approximate it. Okay, so now coming back to what I was talking about, the mean is simply NP. So you can see 50 times 0.3, which is 15, and then my variance is NPQ. So it goes 50 times 0.3 times 0.7, which in my case is going to be 10.5. And I need to find, but remember, it's not the variance that I'm after standard deviation. My standard deviation is simply square root of 10.5, which turns out to be somewhere along the lines of 3.24. Okay, so I got what I needed. So I needed my mean and I needed my sigma. I got those two things out. Okay, so now let's come back to the question. So the question says, find me the probability of x being between 19.5 and 20.5. Okay, so now I know my mean and I know my standard deviation. I can standardize this. So here's how we do it. We go 19.5 minus the mean, which was 15, and divided by square root of 10.5, or rather, because we already found it out, 3.24. Okay, and then now we don't write x anymore. This is z. This is going to be 20.5. Again, minus 15 divided by 3.24. Okay, so now we can actually start talking about the standard normal distribution. Okay, and that's where the tables are. So if you're doing a course where the tables are given, you have to do this, right? If you're doing a more statistical course, maybe you can get away with doing this, but it's good to know, all right? Okay, so that's the usual way of doing things. So this is saying probability of z being between 1.39 and 1.7. Okay, now we can look this up in a standard normal distribution. So I'll show you how to do that. Okay, so this is the one that I got from Wikipedia, right? So maybe your table might look like this, where you have the z values at the 0.00, and then you find the second decimal point on the top. It might look like this, where they give you the proper cumulative distribution, or it might look like this, where they start off from the middle and then go to the right. Okay, it doesn't really matter. But just keep in mind that over here it starts off from 0.5, and over here it starts off from 0.0, from 0, right? So it's only offset by 0.5. Okay, so you need to keep that in mind. So just check what your tables, which one is more like. Okay, so in this case I need to find 1.39 and 1.7. So I look up 1.3 and then 1.39 is going to be over here. So it's going to be, in our case, 0.9177. Okay, and I looked up the other value before. So the way that we do this is to go. We should look up 1.7 first of all, right? Because it's going to be the bigger probability. Okay, let me draw this. Let me draw this if this is being a bit confusing. So this is the area that we need to find. Between 1.7 and 1.39. Okay, so that is the area that we need to find. Okay, but if you think about it, this area over here, I can say it's the same as the entire area minus this area. So if I minus from the big green area this red area, I'll end up with this, won't I? Right? This area that will end up with. Because remember, in the normal distribution, they only give you the big one. They're not going to give you between two values, right? So I find the area for 1.7 first, and then minus the area for 1.39. Okay, so the two areas for the bigger one, 1.7 turns out to be 0.9177, and for this smaller area, sorry, it should be the other way around. So for 1.7 it's 0.9554, and for the small area, which is 1.39, it's going to be 0.9177. Okay, so the answer is 0.0377, and that's it. Okay, so that's an approximate